In section 10.3, we're going to look at those parametric equations we dealt with in 10.2, and we're going to look at doing some calculus topics with parametric equations. All right. Now, you might ask, why would we want to do this? Well, first off, if we already have equations in the parametric form, then it allows us not to have to convert back to a rectangular form in order to find things like the derivative or integrate and things like that. And the other case is that sometimes the calculations are much easier to deal with in parametric form than they are to deal with in a rectangular form. And we're going to see that too. Also, it allows us to deal with things that are non-functions. Because parametric equations allow us to graph things like circles and ellipses and hyperbolas, all which are not functions, not something that we can solve y equals function of x real quickly. So because it allows us to deal with non-functions, sometimes it's easier to deal with calculus topics and parametric equations. So the first topic of calculus one of the first topics that we do is dealing with derivatives. Now, a derivative means derivative of y with respect to x. Remember, that's instantaneous y. How much is y changing as x changes? Well, if we have a smooth curve, then we can find the derivative at some point xy. Think of this as change in y over change in x, and derivative means it's an instantaneous change. So change in y, well, how are we going to calculate a change in y over a change in x? We're going to take the change in y with respect to t and divide it by change in x with respect to t. So it's basically the derivative of y with respect to t over the derivative of x with respect to t. And what I mean by that is y is going to be equal to some function of t, so we're going to take the derivative with respect to t of that function. And then x is going to be a derivative with respect to t of whatever the function x is. Now, in order for this to work, obviously our denominator can't be 0. So when we take the derivative of x with respect to t, we don't want that to be 0. But other than that, it's a pretty straightforward derivative calculation. So let's look at an example here. This is example 0. We're going to find the first derivative of the following pair of parametric equations. So we have x as written as a function of t, x equals t squared plus 4t. Y written as a function of t, y equals 2t to the third plus 7t plus 8. This pair of parametric equations, obviously it's going to be hard to solve and get a function of t. In fact, if you graph this thing, let me show you the graph of this thing. Here's what it looks like. You get this weird looking curve, and notice how it actually, once you hit this spot here, it goes back down, and this is not a function. So it would have been very hard and difficult to try to create functions that you could take derivatives of with those equations. So what parametric allows us to do is just to say, well, y is a function of t. So if I'm going to look at the change in y, let's look at how fast y changes with respect to t. And what you end up doing is just taking the derivative of 2t to the third plus 7t plus 8, which is 6t squared plus 7. Okay, so the derivative of the y function goes on top there. The derivative of the x function then would go on bottom for similar reasons. That would be 2t plus 4. And you can see that you end up with a derivative at every point other than when t is negative 2, because negative 2 would give you a 0 in the denominator. So that's what we're doing in this case. That's how we find a first derivative. Now, if you could simplify this, I probably would, but this one does not simplify very nicely. So that's what the idea is. Now, what happens when we take a second derivative? Well, a second derivative is basically just a derivative with respect to x of your first derivative. So what we're going to do in order to get a second or a third derivative is we're going to take our first derivative and we're going to set it essentially as the y equals function. So what you end up doing in the second derivative is you take a derivative with respect to t of your first derivative and divide that by change in x with respect to t. So it's like, how fast is the first derivative changing with respect to x? And the same thing with the third derivative. How fast is the second derivative changing with respect to x? So that's what's happening with the second and third derivatives. Now, the second derivative would have been probably hard to calculate in our example 0, but you can calculate that in the next example in a fairly straightforward manner. So let's find the first and second derivatives of the following set of parametric equations, and then find the values that the first and second derivatives take on when the value for t is 3. Go ahead and push pause on the video, try to do first and second derivatives, and then plug in 3 in each case. All right, so hopefully you went ahead and did that. So first derivative, derivative of y with respect to x. So derivative of y with respect to t from this equation gives you a 3. Derivative of x with respect to t from that equation gives you a 4. So you get 3/4 or 0.75. Okay, now here's the deal. On the second derivative, we'll plug in things in a second, but on the second derivative, what we're going to do is we're going to first on top is we're going to take a derivative of this with respect to t. Obviously, this is a constant. So with respect to t, the derivative of 3/4 is simply 0. All right, so let me write that down. Derivative with respect to t, whoops, of 0.75. That's what we're doing there. And then obviously on the bottom, it's another derivative with respect to x, so it's another 4. Okay, so that's your original x equation. Hopefully that makes sense. Derivative with respect to t of the x equals 4t equation. So on top we get a 0, on bottom we get a 4. All right, so the second derivative is 0. Now this one is not really interesting. If you plug in 3 as your value in your first derivative, you get 0.75. If you plug in 3, you get 0 into your second derivative. So regardless of what you do, what number you plug in as far as t goes, your derivative is always, your first derivative is always 3/4, 0.75. Your second derivative is always 0. And that should make sense because if you actually graph this, you would end up with a line with slope 3/4. Okay, so the first derivative, when you plug in t equals 3, gives you 0.75. The second derivative, when you plug in t equals 3, gives you 0 as well. All right, in fact, that works for any numbers we choose. So let's do another one. Let's take example 2. And I want you to find the first and second derivatives of this equation, and then find the values of the first and second derivative when t is 0. Go ahead and push pause and try these on your own. All right, so hopefully you went ahead and did that on your own. So first derivative, derivative of y is 4. Derivative of x, again with respect to t, is 2t plus 5. 2t plus 5. Now, what I'm going to do the second derivative, first of all, I'm going to take a derivative with respect to t of 4 over, I keep doing that, 2t plus 5. Hit the wrong. I should probably use a different square bracket instead of set brackets. So derivative with respect to t of that. And then we're going to take a derivative with respect to t of, well, x again. So that's going to be t derivative of t squared plus 5t plus 4. All right. So that's the idea. Derivative with respect to t of the first derivative, 4 over 2t plus 5. And then derivative, oops, I should have said that. Derivative of x. So derivative with respect to t of t squared plus 5t plus 4. Okay, so that's the idea. Now, in the numerator, the derivative of this thing is, I believe, negative 8 over 2t plus 5 squared. Derivative in the denominator is 2t plus 5 once again. So notice we can simplify that if we'd like. That's negative 8 divided by 2t plus 5 cubed in the denominator. So that's one way to write it. There's other ways as well, but that's the idea. So second derivative, oops, is that. Now, when t is 0, all we have to do is plug in 0 in for t. So into the first derivative, when t is 0, we get 4/5. By the way, the special notation here that you can be using, I put just dy over dx equals 4/5. Some people will write a line here and write t equals 0 underneath, but this is fine as well. That line looks like the following. Let me draw it. So sometimes people will put something like this, and then a t, whoops, t equals 0. So you've probably seen that before. Oh, that's a little more green than black, I guess. But you guys have seen that, I'm sure. So anyways, I'm not going to write that because it doesn't have a nice key that I know of how to do that on my Word document. So anyways, that's the idea. Same thing when you plug in 0 into the second derivative. All you have to do is plug in 0 for t, so you end up with negative 8 over 5 cubed. So negative 8 divided by 5 to the third power, which is negative 8 over 125, if you want to say it that way. So there you go. Plugging in t equals 0, not a huge deal, hopefully. All right, so here's what I'd like you to do. Take what we know about derivatives, and with the derivatives that we just found, let's use the information to find anywhere we have vertical tangents or anywhere we have horizontal tangents. So if you think about vertical tangents happen when we're at a point where the tangent is straight up and down. So we're at a point like here I have for instance, an ellipse. This is not the equation of the thing we just dealt with, but it's pretty easily seen on the ellipse that we have a vertical tangent here, vertical tangent here. It's basically when the slope of the tangent line is undefined. So in our case, for instance, if you look at the x equals 3 line, that is a tangent line for this point 3, 0. And it's vertical here, meaning that the slope at this point is undefined. Now, if I were to have written, I think it's y equals 6, a tangent line up here for the point 0, 6, well, that's a tangent line which is horizontal, and we know horizontal tangent lines, the slope is 0 at that particular point. So basically, when we say find vertical and horizontal tangents, what we're asking for is to find when the slope is 0 and find when the slope is undefined. So let's go and do that. Obviously, when t was equal to 0 in our situation, it was not, the slope was not 0 and the slope was not undefined. So let's cancel that, or let's X that out and go back up and say, well, when is the slope 0 or when is it undefined? Well, this forces the first derivative to be 0. So when is the slope 0? Well, it's when this first derivative is 0. So all we have to do is take this first derivative, which in our case is 4 over 2t plus 5, and set it equal to 0. Now, what values of t does that happen for? Well, it never happens for t. There's no value for t in which you can make that fraction 0. So the slope being 0 never happens. And so that means that there are no horizontal tangent lines for this graph. Now, when is the slope undefined? Well, it's undefined when the tangent we're dividing by 0. In other words, it's undefined when the denominator, 2t plus 5, is equal to 0. And this does happen. This happens when t is equal to, now you can write this as negative 5 halves or negative 2.5 or whatever. But the slope is undefined when t is negative 2.5. So we have a vertical tangent when, whoops, t is equal to negative 2.5. And what that means is that there's a certain point on our graph, specifically the one where you plug in negative 2.5 in for t, where we're going to get a vertical tangent. Now you could figure out what that point is by just plugging in the negative 2.5 into the x value and then the negative 2.5 into the y value. When you go ahead and do that, you end up with a negative 2.25 as your x value and a negative 10 as your y value. So you get a vertical tangent when t is negative 2.5, and that happens at the point negative 2.25 comma negative 10 on the graph. All right, so that's the idea. Hopefully that all makes sense. So you can do the very similar things that we've dealt with before, like horizontal, vertical tangents, first and second derivatives, all in parametric form. So here's what I'd like you to do. We're going to do a couple more examples. I'd like you to push pause and find the first and second derivatives of these two functions, or this pair of parametric equations here, and then find the values when t is equal to 0. All right, hopefully you went ahead and did that. So x is 20t, y is equal to 1200 e to the t. So when you take your derivative of y with respect to x, take the derivative with respect to t of 1200 e to the t, you get back 1200 e to the t. Derivative with respect to x is 20. So you go 1,200 e to the t divided by 20. You end up with 60 times e to the t power. All right, it's real nice that the derivative of e to the t is e to the t. So now for your second derivative, you take 60 e to the t, and then you take a derivative of that. That's going to be in your numerator, so that's just 60 e to the t. And then a derivative, once again, of x is in your denominator, so you end up with 20 in your denominator. 60 over 20 is 3, so you end up with 3 times e to the t as your second derivative. Now when you plug in 0 into the first derivative, e to the 0 is just 1, so 60 times e to the 0 is just 60. And into your second derivative, 3 times e to the 0 is just 3. So as far as your first and second derivatives go, when you plug in 0, you get 60 as your first derivative and 3 as your second derivative. And that's it. That's how to do first and second derivatives. Now, one thing that's kind of nice is that even when we have harder problems like hyperbolas, for instance, we saw that when we dealt with secants and tangents, we ended up with hyperbolas. I should say secants and tangents like we have here, we ended up with hyperbolas. So you could, we can, without having to convert into a rectangular form, find first and second derivatives of this hyperbola using these parametric equations. So go ahead and find the first and second derivatives in this case. So here we go. We have x equals 2 plus secant t, y equals 1 plus 2 tangent t. First derivative of y. Well, 1 is going to, when I take the derivative, go away. Plus 2 times tangent t. Well, derivative of tangent is secant squared. So it's going to be 2 times secant squared of t. Similarly, when you take the derivative with respect to t of x, the 2 goes away, plus secant t. The derivative of secant is secant times tangent. So you get secant t times tangent t. Now, one of the secants is going to cancel out in the numerator and the denominator. So you'll end up with 2 times secant to the first power of t divided by tangent. And if you think about what that means in terms of sines and cosines, that's like 2 over cosine, and then tangent is always sine over cosine. So you get 2 over the cosines, cosines are going to cancel each other out. So you get 2 over sine, which is the same as 2 times cosecant of t. So the first derivative is 2 times the cosecant of t once simplified. Now, as far as the second derivative goes, it's a little more complex, but that's all right. We'll take the derivative of that thing we just got, so derivative with respect to t of 2 cosecant t, divided by dx over dt, which we know is secant tangent. So if you take the derivative of cosecant, you get negative cosecant times cotangent. So you get negative 2 times cosecant times cotangent over secant times tangent. Now, if you think about what that means in terms of sines and cosines, whoops, get rid of that. Cosecant is 1 over sine. Cotangent is cosine over sine. Secant is 1 over cosine. Tangent is sine over cosine. And you move everything around, there'll be cosine and that cosine and that cosine all go to the numerator when I multiply. This sine, and this sine all go to the denominator when I multiply. So you get negative 2 cosine to the third divided by sine to the third. Now if you do cosine over sine, that's cotangent, obviously. So that's like saying negative 2 times cotangent to the third power. And that's your second derivative in that case. So that's how we would take derivatives. Here it was a little bit more difficult because we dealt with a lot of simplification, some trig simplification, and all that kind of stuff. But that's the general gist of it all. Now you can take first and second derivatives of any functions you want. Let's do another example here, example 5, where it asks us to find all points which have vertical and horizontal tangents. Notice that you only need the first derivative in order to do this. So I want you to go ahead and do that using x equals cosine t, y equals 2 sine of 2t as your parametric equation. All right, so like I said, x is cosine, y is 2 sine of 2t, right? That's what we had here in example 5. And so derivative of y here, derivative of sine we know is cosine. So derivative of sine is cosine of the same argument. But since this argument is not just t, since it's 2t, I have to multiply times the inside derivative. So if you multiply by the inside derivative of 2, you end up with a coefficient of 4. So you get 4 cosine 2t. Now the derivative of x is simply negative sine. So there you go. Excuse me, negative sine of t. And so now we're going to look for vertical tangents and horizontal tangents. And we know vertical tangents happen when the slope is undefined. We know that horizontal tangents happen when the slope is 0. And so all we have to do, when is the slope undefined? Well, when the denominator is 0. So all we have to do to find our vertical tangents is set that denominator, negative sine of t, equal to 0, and then solve for t. Horizontal tangents, well, we need this entire fraction to be 0. By the way, it's easier to think of that entire fraction being 0. I'll solve that in just a second, but I do want to mention if that entire fraction is 0, just multiply both sides by sine of t, and what do you end up with? You end up with that thing is 0 when the numerator is 0. Okay, multiply both sides by negative sine t. So we'll solve, to get our vertical tangents, we'll solve this one. To get our horizontal tangents, we'll solve this one. Now it does require me, for the vertical tangents, let's focus on that first, to understand how sine works. This is clearly 0 when the sine of t is 0. And we all should know how the sine function works. When does the sine, what do you plug in for sine to give you 0? We're going to make sure you're in radian mode, but we all hopefully know how the unit circle works, or how the graph of sine works. So you take sine, when is it 0? Let's do y equals sine t. Well, it's 0 when t is 0. It's 0 when t is pi, when t is 2 pi, when t is 3 pi. It's 0 when t is negative pi, or negative 2 pi, or negative 3 pi. So y equals sine t, or sine of t is 0 whenever t is a multiple of pi. So t is equal to, a lot of times people say k times pi, where k is an integer. All right. So there you go. That's when we get vertical tangents. Now these things are going to happen a few times, and because our function is defined this way. A lot of times people will focus on values of t that are just between like -0 or 2 pi or negative pi and pi, whatever they focus on. So that's what that's when t that's when we have vertical tangents, is when t is equal to k times pi. Well, when are we going to have horizontal tangents? Well, similarly, divide both sides by 4 here, we get cosine of 2t equaling 0. Cosine of theta is equal to 0. Let me write this down. Cosine of theta is 0 when your angle, theta, that's how we say it, is equal to, well, think about what sine versus cosine does. Cosine just shifts over. And so we get here at pi over 2, 3 pi over 2, 5 pi over 2, negative pi over 2. So basically it shifts it over by pi over 2. So if you think about this, when the angle is k pi plus pi over 2. So basically we just have to shift out all of the things over by a factor of pi over 2. Okay? Now, by the way, our angle here is 2t. So what's that mean about 2t? That means that 2t, whoops, has to be equal to some integer times pi plus pi over 2. Dividing both sides by 2, you end up with seeing that t has to be k times pi over 2, where k is an integer, plus pi over 4. So that's the idea. That's when we get horizontal tangents. Now, if you want to look at this in a slightly different way, you can look at the actual graph, cosine 2 sine 2t. And what you'll notice is you get horizontal tangents out here, like we said. Well, I don't have a slider for that, but I could create one. Let me do that. There we go. So notice when a is 0, we end up right here. It's hard to, well, maybe it's not that hard to see, but we end up with something that's right there. You start sliding it over, it goes up, down. When do we get to our next vertical tangent? Well, it's right about when a is pi, and then we come back around, we do another loop, and we get back to our starting point when a is about 2 pi. It's hard to see there, but when a is about 2 pi, you see we get close to the starting point. If I had steps of the right size, it'd look even better. And then the same thing. So coming back around, when do I have vertical tangents? Well, basically they're at these two spots, this spot here and this spot here. One of them is when t is 0, other is when t is pi. And then you go back around, once you get to 2 pi, you get back to this point right here. And you could go in the negative direction as well. Well, when do we have vertical? That's when we have vertical tangents. When do we have horizontal tangents? Well, at this point up here, at this point, at that point, and at that point. We have 4 different horizontal tangents, and you can see, it's kind of hard to see right here, but roughly 0.8, that's exactly our first pi over 4. And then you go add pi over 2 to that, add pi over 2 to that. You're going to get at this spot right here. Add another pi over 2 to that, you get at that spot. Add another pi over 2, you get back here, and then all the way around, and you get back to your initial horizontal tangent. So you actually have 4 different horizontal tangents, but because of the way you trace the curve, this goes around forever and ever and ever. So you have infinitely many values of t, but there's actually just 4 spots on the graph. So that's how we deal with derivatives stuff.